In this example, we're asked to find the value of x that makes timeline 1 and timeline 2 equivalent to one another. To do so, we're going to use three concepts that have been discussed in class. One concept is the idea that a timeline can be converted to an infinite number of equivalent timelines. A second idea is that in order to compare two timelines, we must either bring money to the same point in time or spread it out over the same period of time. And the third concept that we'll use is that money can be moved around in time if the interest rate and the number of years are known, using the factors that we've derived in class. Let's get started. Our general approach is to set timeline 1 and timeline 2 equal to each other and solve for the unknown value x. In order to compare two timelines or set them equal, however, we must first establish a common basis. I'm going to convert timeline 1 to an equivalent timeline and do the same thing for timeline 2, and then set those equivalent timelines to each other. In order to compare the two timelines, however, they must be compared at either the same point in time, the present, the future, or spread out over the same period of time, such as a uniform payment series. My approach to this problem is to bring everything back to time 0 and determine the present value of timeline 1, and similarly do the same thing for timeline 2, bring it back to a present value. These new equivalent timelines can then be set equal to each other. The first step in the solution is to calculate the present value of timeline 1 by bringing all values back to time 0. We start with the minus $150, which is already at time 0. We can add to this the $44 once it's brought back to time 0 using a P over F factor at 5% interest and bringing it back one compounding period. We then can use another P over F factor to bring the $70 back, where the P over F factor is used at 5% interest and 1, 2, 3 compounding periods. Lastly, we have the minus $28 in year 6 that needs to be brought back 6 compounding periods. I'll speed up this next part of the video where we're essentially plugging into the equation that we have for P over F using 5% for I and the appropriate value for N. Substituting into this expression and solving, we see that the present value of timeline 1 is negative 68.522. For timeline 2, again, we want to calculate the present value of the timeline, and we need to do so by first bringing the $120 back using a P over F factor. Looking at the timeline, we see that the $120 needs to be brought back one compounding period. Using a P over F factor, where I is equal to 5%, and N would be equal to 1 year or one compounding period. Now we also have the value of x in the equation. Again, scrolling back up, we see that x is there in year 5, and it must be brought back 1, 2, 3, 4, 5 compounding periods to get it all the way back to time 0. We'll use a P over F factor, where I again is equal to 5%, and N in this case is equal to 5 years or 5 compounding periods. Again, we'll speed the video up as we substitute in the value of 5% for I and the appropriate value for N into the expression to solve for the present value of timeline 2. Since x is unknown, the present value of timeline 2 is expressed as a function of x. Now what we know is that timeline 1 and timeline 2 must be equal to one another, so we set the present values equal to each other and substitute in the present value that we found for timeline 1 and the present value that we found for timeline 2. Now we have one equation and one unknown, and we can solve for x by first moving the 114 to the other side and dividing by 0.78. Doing so, we find that the value of x is negative 233. We can repeat the same approach for parts B and part C, where the only difference is the value of I in the equations that we developed above. Solving for these, we find that for part B, x is negative 268, and for part C, x is negative 366.